Yo, yo, yo. What's up, what's up? Welcome back. Today we're working on my x86 operating system, Stream OS. It's an operating system I'm developing on Stream. Yeehaw! So this is like just a kind of toy operating system, written for like fun, learning, whatever you want to call it. We're making an OS, seeing how it looks. So we've gotten pretty far. So far, we have like a kernel. Oops, hold on. We have like a kernel that we can boot in QEMU, a virtual machine, and it runs like this like shitty little demo. So we have like keyboard input. We have like this shitty little games. We can play Brick Breaker, which proves that we're like doing input and we're writing to the frame buffer and drawing pixels and stuff. And I can talk to it over TCP. I think it's, what is it? Netcat, how do I use this? Oh, I have to put the port as well. And I have to say like, hello, test, hello. My virtual machine, he like sees that data come in and he sends it back. So we've got like some sort of like Ethernet stack working, which involves like ARP, UDP, TCP, PCI in order to interact with the Ethernet card. We've got graphics keyboard. And like we've also got like the bones, so we have like booting, we've like got some form of concurrency. We're like playing the game while we're doing TCP stuff, and we've got like this like input output that's going to the serial console that like QEMU, the virtual machine, is forwarding to our input output. Great, we're starting to do stuff. And what we've been working on for like the past, I don't know, maybe a couple weeks, it's been a while, is we've been kind of like working towards multi-core support. So we initially assumed that everything was running on single core, and so we had to do a lot of stuff like set up our mutexes, set up our like everything to be used between multiple threads, stuff like that. And then we like booted the secondary CPUs, so we can now run an arbitrary function on there. But we still have like a couple places where the like initial assumptions of non-multi-core are like kind of biting us in the ass a bit. Specifically, our memory allocator is not multi-core safe, which is causing problems in some cases right now. And so the first thing we're going to do is we're going to just like quickly patch over that. And then what I wanted to do is our... let's see if I can like show this right now, actually. So when we run our our little demo, if I run it with num cores set to 2. So we boot like a second CPU alongside the first one. We do say that we boot the CPU and we found some info for it, and we say like hello from CPU 1. But if I look at QEMU, we have like one thread that's just running at like max CPU. He's just like spinning, like, oh, is there anything to do? No, shit, there's nothing to do. I'm gonna keep going. Anything to do? Yeah, now. And then he, when he gets a function, he runs it. And so what I want to see if we can figure out is how to make it so that the secondary CPUs don't do that. The mechanism that we're using on CPU 1 is we execute this like CPU instruction halt. And he basically says like, don't fucking do anything until we get an external interrupt, which works great for our single core situation because every action that can happen triggers an interrupt. Like a TCP packet comes in, boom, interrupt. I press a button on the keyboard, boom, interrupt, right? And so it's like really sick. We can just kind of like say halt and then go like, okay, I'll check later. And when I get that interrupt, then I'll start doing work again. But we're not like using interrupts on our secondary CPUs because we were too lazy to set up some of the like inter-processor multi-core dispatch stuff. We're kind of handling all interrupts on CPU 1 right now, and we probably will until I feel like taking on that complexity. And so yeah, we want to look into how we could intelligently wake up our secondary CPUs without interrupts, without using this like halt trick. So that's the goal for today. And I think let's just start moving and grooving. Okay, so the first thing we wanted to do is fix the broken memory allocator. Great. So last stream we did look at this. And we didn't really get to the end. We didn't get to like a very nice spot, right? We said, title of the video is, we failed to implement a lock-free memory allocator. I kind of thought that if we just, when we tried to implement a lock-free queue, it was pretty easy. We just kind of like guessed what the right sequence of actions would be, and it seemed to work pretty well. But for the memory allocator, it turns out that it's like a little more complex than that. I was looking up like lock-free memory allocator, and basically found this like paper from IBM. Is it this one? Give it a sec to load. And the short version of this is that it's not simple, like at all. Specifically, like these like malloc implementations are like, it's not just use some atomics in the right spots, like I originally thought it would be. So what I think we can do instead is if I go into my allocator, I think we can get away with just doing everything we were doing before, just behind a giant mutex. And I know last stream I was saying a mutex is not okay, right? If we use a mutex, what happens if we interrupt and we're trying to allocate from an interrupt handler, and all of a sudden like we can't because the mutex is locked when we interrupted? But you could just say, well, I'll disable interrupts as well when I allocate. Fuck it, blaze it, you know? And I think that's not like nearly ideal, but I think it's probably plenty good enough for now. So I think what I'm going to do is I'm going to say, let's add a lock here, and we'll make it a spin lock. And spin lock protects nothing. We would usually protect like a variable, but because the way that this like allocator is set up, it makes more sense to just stick it outside, I think. And then here we'll say we're going to use our utility classes, and one of them is going to be our interrupt guard. And one of them is going to be our spin lock. Great. So our spin lock needs to exist. So we'll just quickly make one. And then just when we start our allocation and deallocation, we just lock the lock. So self, lock, lock. And before we get that, we have to disable interrupt. So the way we disable interrupts right now is like through like this like guard thing that we use. We say let interrupt guard, or guard, we'll call this guard 2, I guess, or guard 1 and guard 2. He is a interrupt guard. No. So he's similar to the mutex, where he's supposed to guard a resource, but again, we're just going to ignore that for now. And then we'll just say guard 1 lock. And this will just disable interrupts. And so now I think our allocator should be thread safe. And just to prove it, we'll make like a pretty easy test here. What we'll do is we will go into our functions that are running on all of our CPUs, and we'll just stick this in a loop. And probably we should sleep here as well, just to make sure that we don't like flood our logger so much that it can't service the stuff in time. So let's just quickly shove this in here. Oh, this is not async. Right, this isn't an async function. So we have to actually we have to like calculate the sleep manually. So we'll say that the end of the sleep is the current time plus 100 milliseconds times the tick rate. And this is as f32, and this is as usize. Cool. And then here we just say while the time is less than end, we do nothing. And this needs to be a moved thing, and then we have to say, we stash the time. So we say equals arc, clone, self monotonic time. Great. Cool. Almost there. This should compile. Great. So I think this should, if I say like run with 3 cores, I think we should pretty much guarantee a panic, like an OS crash by doing this. Great. Yep, we sure do. And now if I go into my allocator and I re-enable these guards, we should start seeing this work. Give it a sec. Yep. Right, so that's a pretty good indication that this is working correctly. Now, there is a little bit of a bug in here where our interrupt guard, I'm like pretty sure, might re-enable interrupts on the wrong core. We only want our interrupts to be guarded on core 0. And so there's like a better fix for this. Like we could like implement thread locals and like track interrupt guards on each CPU directly. But instead, what I'm going to do for now is I'm just going to make sure that our interrupt guards are only ever doing anything on the bootstrap processor. So here I'm just going to say assert that the bootstrap ID is 0. We're going to say, I guess we're going to say pubconst bsp ID is a U8 is equal to 0. And the reason I'm doing it this way is because then in my interrupt guard stuff, I can just say, if CPU multiprocessing CPU ID is equal to multiprocessing bootstrap processor ID, we do this stuff. And we do the same for this. That way we make sure that we are only we're only messing with interrupts when we need to. Cargo check. Cargo run. And let's just see. Yep, everything seems to be still working okay. Interrupts are being handled fine. Yeah, I think everything's okay. So that's just like the quick fix and end for last stream's topic. So let's just say that this is done at around 1320. And now let's just commit that real quick, I guess. And I'll say what? Quick fix for memory allocation threading issues. Okay. Okay. Cool. And then let's move on to the real goal of today's stream, which is letting the secondary CPUs take a nap. So what does that look like? So what I stumbled across here were these like monitor mwait commands. And the idea behind these is you can say, hey, CPU, take a nap. And if somebody touches this area of memory, it's time to wake up, essentially. So I did a little bit of playing around with these instructions off stream just to make sure that I like understood what they did. But I think it's probably makes sense to go through that process again and then use them to do something useful. So let's go over here and we'll go back to our like secondary CPU stuff. And let's like look up these monitor mwait instructions. And here we have a little bit of an example here where you basically say, where do I want to look this up? Maybe I want to look at the monitor command as well. So the way this works, supposedly, is you call this monitor command, and he says, like, hey, here is the memory range that you care about. And I think that I saw that there's something about hints in ECX and EDX. They communicate other information. So you put the address of where you want to monitor in EAX. In ECX and EDX, you put in extensions and hints. It does not change the architectural behavior of the instruction. No extensions or hints are defined. Undefined hints in EDX are ignored by the processor. Undefined extensions in ECX raise a general protection fault. So in the example I saw, you just write zeros to these guys. And then you just type monitor and you type mwait. So it should be something like or arch ASM monitor mwait. This should be all we have to do. And then we just set our registers. So we say in EAX is equal to like the address that we want to monitor. So we'll fill that in a sec. ECX, we're going to say 0. In EDX, we're going to also say 0. And now we have to set an address. So probably what we'll, let's like for our initial thing, maybe we set like a like an atomic bool that we share between threads. It's false, right? And we can say like while B load ordering relaxed. Ordering relaxed. While this is false, we monitor the address of the bool. And so that we say let B adder is equal to what? And star B to like dereference the pointer and then get the address of the bool. So this should be the type of reference atomic bool, and let's just as const or as mute atomic bool, I guess, const atomic bool. And then we can say we monitor the B address. Now we need to make sure that we handle like this like movement of stuff correctly. So we'll say let B is equal to arc clone B because we're sending it to a different thread, and so we need a different version of it. And then down here, let's like wait for a little bit. So we'll say sleep for maybe like 3 seconds. And we'll take in self monotonic time and self wake up requester. And we wait for that. And then we'll set the bool to true. So we'll say store true with ordering relaxed. We don't care about the memory around us, just the bool itself. And so now, what we should see is that we should see nothing happen here until the Boolean is set. Now, even if this monitor and mwait wasn't working, we would still see that. So here I say like cargo run release. And we should see, actually let's make some logs here. Let's just say info sleep finished. Just so that we get the some visible effect here. So here, somewhere we see sleep finished, and then we see this like hello Mick from CPU1 spam again. Let's take this out of a loop because fuck that noise. Yeah. And if I look at like my top output, I should see like, yeah, my CPU's railed in this time, right? I'm seeing like 200% CPU before the sleep is finished. And so what I hope to see is if I uncomment this like monitor mwait stuff, I hope to see that the CPU usage drops significantly in that period of time. So cargo run release, start monitoring here, and I actually start seeing, so I will admit that I cheated here and I saw this off stream already, but I just see like hard boot looping. And the question is like, why? Why the fuck? And so we can start trying to like bisect the problem, right? So we can say, is it the monitor command or the mwait command? So if I just comment this out, the mwait, the boot looping still happens. So it's fucked. And if I comment out this monitor command, the boot looping should stop. Okay. So then the question is, what the fuck, right? Why the fuck wouldn't this work? And if I read this a little closer, I can see that the CPU ID can indicate the availability of monitor and mwait in the processor. So there might be a processor where these things don't fucking exist. Now, this was introduced back in like Pentium 4, I think I saw somewhere. Pentium 4. So it's like we should have this. And so I was looking up like, well, first let's look at like if we can extract that information. So let's look at CPU ID x86 and see if we can find where we would find the information. So he says it should be an ECX bit 3. And so, and I think the format of this is like we say when we call CPU ID with EAX set to 1, I think if I remember correctly, there's like multiple modes that you can call CPU ID with, and you like set one of the input registers to determine what the outputs will be. And so I think this is saying that when you set EX to 1, you should be able to determine if you support the monitor bit. Great. And so let's see if we can confirm that in some docs somewhere. Okay, so initial EAX value 1H. And so somewhere we should be able to see what we get back. So we should be able to get initial APIC ECX feature information, see figure 3.7. And so we should see bit 3 here. Cool. So if we set EAX to 1, call CPU ID, and look at the value of ECX, we should see bit 3 set. And so we can do something like this. Instead of doing all this shit, fuck this noise. Comment this out for now. We'll just say core arch ASM, and on this CPU, we're going to execute CPU ID. And we're going to say that our input of EAX is 1 to put us in that mode. And we're going to take out ECX as of variables. We'll just say let ECX is a U32 with a, and we'll get them out here. And then we also have to specify that EBX is going to get modified because the CPU ID command or instruction is going to like set all of these registers, and you're also going to set EDX. And we have to tell the compiler this so that if he has something stashed in ECX or EDX or EBX, he doesn't go like, oh, I expect that to be what I had before. No, we have to tell him you are going to get fucked up. And this just goes to nothing, and I think that's it. And then we can say invalid ASM output cannot assign it to this expression. So this is in, I guess. And late out EAX, I think, is the other syntax. There we go. And then I think that we can say printline ECX monitor bit, and we can say ECX get bit 3, I think is what they said it was. And I think I need to use my little utility class. So it's util bit manipulation get bits. And this is just like a trait that makes it easier for me to like pull out some specific bit instead of having to do like the shifting and masking all by myself. I fuck up that shifting and masking like every single time I do it, so I've just like added this little trait that does it for me, right? I've like get bits does like masking and shifting, blah blah blah. Okay. So if I cargo run this now, we won't. We see that we got the ECX monitor bit set to false. And I'm just going to change this to info logging because there's like a race condition in our print line implementation. So I'll just use info logging so that it gets like serialized to one thread so they don't clobber each other. And so the question becomes like, well, why the fuck is this set to false? And I did some Googling and testing before stream. And if I understand correctly, it's this could be disabled by the BIOS. But in the case of QEMU, I think like QEMU monitor mwait. I think I saw somewhere that it's disabled by default. Yeah, here they're saying like allow monitor mwait CPU ID override, and so they're saying like KVM allows trap and emulate, but without that, then it's like you'd just be spinning on the CPU. So it's like, what the fuck is the point? It's better to flag to the operating system that you don't support it, so the operating system tries to do something more sane. But we can just enable KVM, and I don't really know what KVM is. I think it's like using some sort of like Linux protocol to like interact with the kernel in a way that like gives extra capabilities that you wouldn't normally have. I'm not really sure. I don't really know why, but if I type in like into my QEMU wrapper, I think it's like enable KVM, and then I run this. I thought I saw, okay, when I tried this earlier, I thought I saw a change in behavior. So let's just try running this monitor command. I think I saw that this stopped crashing. It does. So then the question is, why is that monitor bit not set? I didn't actually try checking the individual bit last time. I did just try printing out ECX and seeing I did see like a change in it. So let's try that. So let me just disable this monitor call again, and we'll run this this way. So we see 802.0.0.1, and I did notice that if I go back into my wrapper script and disable KVM, this number is different, right? We have a bit set that we didn't have set before. Now, I don't understand why this isn't being set. What number is being set? 802.0.0.1. Hold on, let's go back and look here. Feature information returned in ECX. Yeah, I'm not getting it. So here, we're actually not seeing a change in ECX. However, we are seeing that the monitor command just starts working. So that's kind of weird. I don't really understand why that is. But it must be that I'm not calling CPU ID correctly. Input EAX 01H returns feature information in ECX and EDX. And the information in the ECX register should say that the monitor command is supported in bit 3. Which just doesn't really seem like what we saw. But let's... Unless, so we saw 800 go to 802. So, like, what is that flag being set? Python 3, we can just print this number as, let's just see what that bit is. So we'll say format, this is Boolean, which I think you should write like :B in here. And that's, 1, 2, oh my gosh, 1, 2, 3, 4, or sorry, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, or something, somewhere around there. So if I do this, shifted right by 20, 21. Yeah, so this is bit 21. So they're saying that they support X2 APIC is the only difference that we're supposedly seeing, but we're seeing the monitor instruction no longer crash our CPU, so it must clearly be supporting it. Okay, whatever. Let's check if here. Hold on. Let's go back to the QEMU wrapper. Enable KVM again. Cargo run release. Okay. And here, let's look at the CPU usage again. And go back into main and look up monitor. This stuff should be on again, and then this stuff should be logged. And so what I want to see is for the first 3 seconds, I want my CPU usage to be not that high. That's what I want to see. And I'm not seeing that. It is like 200%. Which is lame. Very lame. Let's do something like set this to 10 seconds. And maybe we can maybe info log that we looped here. Because really we want to see that this like waits for something interesting to happen. Okay, so that's a problem. We are still hot looping here. We are still hot looping. So maybe when I enable KVM, the instruction like doesn't fucking crash, but it's still not supported. Like maybe the behavior is just changing. Which is unfortunate. I was kind of hoping that this was my way out. I was kind of banking on this command working. QEMU enable monitor mwait. It does say that KVM does now support it. Fully supported in the guest. User space still doesn't have the option to mask these features off. Maybe I have to enable them manually. I think that I also saw somewhere that the BIOS can disable those features. So BIOS disable monitor mwait. I saw somewhere some assembly code to re-enable it. So this. Where did I see this? I saw this guy. Where the BIOS could disable monitor mwait. Here, this is it. And this guy is claiming that you could re-enable it. So let's see what happens if I do that. Now that KVM is enabled. Okay. So here we are reading and writing this register that has these like specific permissions, blah, blah, blah. And basically this is supposedly supposed to re-enable the mwait command. So maybe if we do this, we'll just say these have modify EAX, modifies ECX, modifies EDX, and it doesn't look like it touches EBX. So let's see if that changes my CPU ID at all. Doesn't look like that enabled it. And does it look like our CPU usage has decreased at all? No, our CPU is still just like spinning like mad. Oh, but maybe it's not as much as we thought it was. Num CPU's 5. Oh, that is just like spinning at like 400% still, which is bad. Lame. Okay. So it does look like we are failing to set the monitor mwait stuff. I wonder if there's like a QEMU thing that we can configure it with. So QEMU, enable monitor mwait KVM. This is a lot. Oh, here. I can expose monitor mwait by setting some CPU properties, it looks like. So maybe in the QEMU wrapper, I think it was like CPU mwait. QEMU has a CPU flag. I wonder if it changes if you do CPU host. That sounds reasonable. Oh, okay. That does look like hella different. Hella different. It does still look like my CPUs were just fucking spinning there. Which is annoying, but that does look a lot different. Let's look at what, if we get bit 3 from ECX now, does it at least claim that it's true? Does it at least claim? It is still claiming that that's not set. But I think I saw somewhere that you can like force enable it. Oh, maybe I put comma monitor or comma mwait or something. Man QEMU system. Is there like man QEMU? There we go. Mwait monitor CPU. I think I like CPU features maybe. Where is this coming from? Let's pull open the QEMU source code. That'll probably be easier. Okay, so this patch is claiming that they have, like, expose monitor somewhere. Oh, maybe that's not actually in here. KVM. Oh, so maybe this actually isn't merged. Mwait. Yeah, maybe this isn't in what I have. Or maybe this wasn't merged. That seems like very possible. QEMU at monitor mwait. I was hoping, really hoping that I could avoid setting up interrupts on the secondary CPUs. But if this doesn't work, then I am kind of fucked. Yeah, it does seem like maybe this just wasn't merged. From OSDev wiki, in order to allow SSE instructions to be executed without generating a UD, we need to alter the CR0 and CR4 registers. I believe those are SSE instructions. What's like UD? OSDev wiki SSE, is that where you're getting this from? Or maybe I can look up like monitor here. Do they have like mwait in here? I don't see anything on OSDev wiki about mwait specifically. You are saying that those are SSE3, and I think I saw that as well. I think I saw that those are SSE related in some way. Maybe I saw that here. Monitor mwait and SSE3 for thread synchronization. So you must have seen that on the OSDev wiki from the SSE page. It's weird though because when I looked at like the CPU ID stuff, I'm pretty sure SSE3 is set, but the monitor value is not set. So maybe this is just a dead end. Maybe. Oopsies, I'm in the wrong tab. Where was I? Here. So yeah, it is possible that this just is not where I want to be. It's possible that like enabling KVM fix this, but fuck. So what does I was looking up monitor mwait, and people were saying like, oh, Linux kernel uses monitor mwait in the auto loop. But I guess that's not in all cases. Maybe that's only in cases where it's supported. Otherwise, the instructions are put in any logical core. Yeah, that's unfortunate. So I guess if I want my CPU to not hot loop, I do have to work with probably the long-term thing I'm going to do is I'm going to enable the APIC send interprocessor interrupts and just use halt again. I guess like what happens, let me think. So the other mechanism that we could use is we could try doing something like actually let's just mark this as monitor mwait initial testing, and we'll say that we kind of gave up on that at around like 41, 45. And the next thing to do would be like experiment with second CPU interrupts. So here, by default, we have like interrupts disabled. And if I were to just like enable them, first of all, do we just like start immediately crashing because we haven't set anything up? Let's do like a cargo run. So nothing's crashing, which means that the secondary CPUs probably aren't receiving any interrupts, which makes sense because we've never like enabled their interrupt controllers. Makes sense. If I try to do something like just execute like an interrupt here, I'm assuming that will result in a triple fault. Yeah, that's just like hot looping my CPUs. That makes sense. And so I guess like the next thing that we would maybe want to try is triggering an interrupt from another CPU. The idea being that when I push a function to this CPU for running, it would be nice if I could execute an external interrupt and cause that to wake me up. So maybe what I'll do here is I'll halt the CPU and I'll say hello. And theoretically, we should see that hello from CPU N never logs. And we're not seeing that. And maybe we could send an external interrupt over to that CPU and just kind of see what happens. So let's sleep for 1 second instead of 10. And let's see if we can figure out how to send an interrupt. So I think I saw in like the Intel Programmer's Guide, Intel System Programming Guide. That's probably what I'm looking for. Give it a sec. It's got to load. In here, if I look at the like interrupt command register. So this is what we're using when we like enable the second CPUs. We like send these initialization interrupts, and those trigger like the CPU to start and stuff. But I think I saw in here we can just deliver an interrupt specified in the vector field to the target processor or processors. So I think there's a way to just send an interrupt. So I think if we look up like APIC IPI interprocessor interrupt. I think that you can just send an interrupt directly. This isn't what I want. This isn't what I want. Interrupt command register. So here, the interrupt one is issued when this is written to, but not when this is written to. Send an interrupt command. One should first write 310, 3 blah, blah, blah. So this isn't really what I'm looking for either. I'm looking for, like, can I just send an interrupt? Okay, so I think if I were to just guess from reading this, we could send this delivery mode fixed, and just set the interrupt number in the vector field. So in here, we just drop the interrupt number. Here we say fixed. And then here we do all the same stuff that we were doing before. Hopefully we should be able to see an interrupt trigger on the other processor, at least maybe wake it up. So let's try saying, let's just try executing that. So in our multi-processing stuff, we already have a lot of like code to start working with these things. So I think I'll just maybe try dropping that in here. So I'll just say pub function. We'll just say send interrupt. And we'll send that to a specific CPU, and the interrupt number is going to also be a U8. And we're going to do the stuff that we did here, where we like take the high and low bits of the interrupt command register. We're going to select the ID of the CPU we're trying to interrupt. And then we're just going to send out this interrupt command. So off screen, I think that if people have been following along, they haven't really seen this yet. Before, we just had these like bit masks from this like SMP page, symmetric multiprocessing. Oops, I just typed in Google SMP OS dev bang G, not GF, whatever that is. And here, we just had these like manual bit masks that they were sending. I've kind of cleaned these up into like a list of commands like that follow the spec here a little better. It says what all these are. So we should just be able to say, let's change the delivery mode from start to fixed, like it says. We'll set the vector to be the interrupt number. And then we can just write that to the interrupt command register. And I think that should be fine. So here we'll just say multi-processing. We'll send interrupt to CPU 1 with interrupt number like 0x80 or something. And the APIC pointer. So here we're going to have to like get the APIC pointer from somewhere. So I guess we'll have to stash it. We'll have to stash it when we get it in initialization. So here we'll just say let APIC pointer is from the ACPI tables. Let's just pull it out. And we'll store this in the kernel. And here we'll just say APIC pointer is a mute U8. And if we cargo check that, that makes the kernel not send and sync, which is annoying. So I think that we just like wrap this is like the pattern I've been doing before. So I just say struct APIC pointer is a mute U8. And I just say this is sendable. And this is syncable. And then I store an APIC pointer instead of this raw mute U8. And I guess while I'm here, I'll just derive copy and clone because I know that that's going to be useful later. So here I call this an APIC pointer instead of just using it directly. And now we have a lot less errors, but it still isn't like the fact that we're transferring a mute U8 over into our thing here. So I think that you could just say, oh, this is just 0. It still doesn't like that because it thinks I'm trying to share mwait, even though I've wrapped that in something sendable syncable. So probably if I say pointer is self.apic pointer.0, hopefully that turns into a copy that doesn't make it over an await boundary, which should coerce this guy into doing the right thing. No, he still doesn't like that. Oi, oi, oi. Like, is it something like this? No. What is he freaking out about? Like, this self-apic pointer is sendable and syncable, so he shouldn't be bitching about mwait. Oh, that's so annoying. So if I comment this out, everything works fine, yeah. Like, does this do it? No. I'm pretty sure I had something that worked here before. I just can't remember what it was. This is so stupid. It's so dumb. Because I think the problem is when it goes over an await boundary. He's saying like star mwait is not sent shareable. Which is fine, because I'm not trying to share the mwait. Ugh. Oh, I think I did this. Aha, there we go. That's the trick. That's the trick. So we copy the thing that we know is sendable syncable, and now it's not being tried to be shared between the threads. There we go. Which is like a stupid workaround, but it is what it is. And so what do I expect to happen here if this works? I guess I expect that halt to come out of, like, I expect the CPU to come out of halt. Right, so we expect to see hello Mick from CPU blank if we got the interrupt. And nothing happened. What happens if we try sending it as like a non-maskable interrupt or something? So here, I think it was delivery mode. We can send like NMI. And how long were we, like, when are we sending this again? We send this after a sleep of 1 second. So we should see a little info log of sleep finished. Which we actually don't see. Which is weird. Okay. So maybe we're just never even sending it. What the fuck is going on? Why are we not seeing that info log? 3. Oh! Oh! Oh, whoa, 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 whoa. That's good. That means that our interrupt is crashing it. I think. Now, I don't understand why that sleep wasn't working for 1 second. That was fucking weird. We're gonna have to go back to that. But yeah, that's looking good. So I guess the question is it only non-maskable interrupts that are causing that? Let's try a non-maskable interrupt, a normal interrupt. Okay, so that's not crashing. And if I enable interrupts on the CPU again, does that cause a crash again? So we wait our 3 seconds, we see sleep finished, no crash, no log. Okay, so probably that indicates that like our interrupt is being masked in some way. And the next thing to do would be try to unmask it. Right, that's, I think. So presumably, our interrupt masking that we've done so far is using like the old programmable interrupt controller, not the advanced version of it. So is like maybe what we're supposed to do is we're supposed to set up our APIC on the second CPU and tell it that we're allowing other interrupts. I think I saw that somewhere in the past. So I think here Maybe not here. Maybe in the Intel programming guide. Like somewhere there's probably a chapter on like Apex. Yeah, here we go. And somewhere in here, I think I saw that you like set up masks. You set up your like interrupt masks here somewhere. Maybe it wasn't here that I saw this. Maybe it was in the OS Dev Wiki somewhere. Where would I have seen this? Okay, so somewhere in our local APIC, we must be able to say, oh, I saw it somewhere. Local vector table registers. This looks like probably what I was looking for. There are some special interrupts so that they can interrupt execute itself. While external interrupts are configured in the IO APIC, these interrupts must be configured using registers in the local APIC. The most interesting registers are the APIC timer and the local interrupts. Okay, but was there where would I have seen enabling interprocessor interrupts? So here they say you set the vector number, you set if the interrupt is pending, you set the trigger mode, and set to mask. So if I remember correctly, in our like initial APIC investigation, we actually printed out the whole table and we saw that everything was masked by default. So presumably there's a way to just set those values manually, which is going to be called vector table, local vector table, machine check interrupt, timer, thermal. But how do I set like the masks itself? Maybe I saw that on the IO APIC. That doesn't seem right. IO table. No, I'm missing something. So you write to this to signal end of interrupt. That makes sense. Local APIC configuration. Okay. So we have memory mapped registers. To enable the local APIC to receive interrupts, it is necessary to configure this various interrupt vector register. The correct value for this field is the IRQ number that you want to map, blah, blah, blah. But how do I... So where does he do that? He write register F0. Oh, so this is just this. Is there nowhere where I can like set a table? I remember iterating a table. Let's look at the maybe multi-boot stuff. Or it wasn't in the, it would be in MADT, the multiple APIC descriptor table. This is probably what we were iterating. Yes. We iterated the sequence of variable length records with enumerate interrupt devices on this machine. Each record begins with this. So this is where we printed all of our entries before. And then I just don't understand how to fix it. Okay, I guess maybe we go back to the Intel programming guide and we just look a little closer. So somewhere they're going to talk about the vector table in here. Let's see if this block diagram has anything about masking in here. Yeah, local vector table. Timer, interrupt, local interrupt 0, 1, performance, blah, blah, blah. So I guess none of these are what I thought. none of these kind of talk about masking. What if I like search mask here? Each entry in the LVT has a mask. So I wonder if it really is the IO APIC that handles this. The local APIC will respond normally to init, NMI, SMI, and SIPI messages. Pending interrupts in IR and ISR registers are held by require masking or handling by the CPU. The local APIC can still issue IPIs. It is the software's responsibility to avoid issuing IPIs through the IPA mechanism in the ICR register if sending interrupts through this mechanism is not desired. Blah, blah, blah. The reception of any interrupt or transmission of any IPIs that are in progress when the APIC is disabled or are not completed before the local APIC enters the software disabled state. Oh. So maybe I have to enable the APIC. Just straight, like maybe that's it. Maybe once we enable it, then we'll start getting the interrupts. So where do they enable it? They just write the interrupt vector. They just set the spurious interrupt vector to start receiving interrupts. Okay. And here they set the base of the APIC. Maybe we can just run this. Like, this seems pretty straightforward. Let's kind of hope that the thing is already mapped. Because it was for the main CPU. So I wonder what happens if in our CPU startup, or maybe just here, we can do it. We can just write so what we can say, let APIC pointer 2 is equal to self.apic pointer. Just hope that this is the same. So we take APIC pointer 2 and we write to it plus F0. We'll say this is the spurious regs equal to this. And what are we going to do with that? We're going to write the value that's in it. So we're going to read it. And then we're going to add or in 0.0.0. And we're going to write that back. So we write it back with this. And what doesn't it like here? Mwait cannot be sent between threads. Fuck off. So what doesn't he like now? Oh, this probably like this like dumb shit. Again, where maybe I have to say like let APIC pointer 2 is equal to APIC pointer 2 or something. Yeah, it is. Oh, that's so stupid. Now all of a sudden I can use this mwait. Yeah, that's so dumb. Oops, this spurious register needs to be probably U32. Yeah, that's pretty funny. Like just this line fixes everything. That's so fucking stupid. Hard to run. And so I guess I'm hoping to see a crash, but I'm not. Oh wait. Ooh. I am seeing a crash. Okay. That's good. And if I don't enable interrupts, do I still see that crash? No. Okay. That's a really good sign. Really good sign. So maybe just by enabling the APIC, I am like receiving that interrupt now. And so now maybe all I have to do is like handle that interrupt like initialize my interrupt vectors. So I think here probably we can just call this init function again. I think that I can, yeah, let's just fucking send it and see. So it looks like we need to create a new IO allocator. This is kind of like fucked, but that's fine. So I'll just this is like the IO allocator is supposed to prevent us from reusing the same registers on multiple places. But if I just create a new IO allocator, you like sidestep all of that checking. So I'm just gonna do that for now for temporary setup. So say IO allocator is equal to IO allocator new. And if I just set up my interrupts again, the idea here is hopefully this generates like a bunch of interrupt stubs and will punch them into the right spot here. I think. I'm not actually sure. There's like a good chance that that doesn't work. Very good chance, but let's just see. What the fuck does that say? Oh boy. Okay, so let's run the GDB. Or let's maybe start with less cores at once. I think I actually have to do something like, what doesn't this like? Oh, this does probably work with the picks directly. Yeah. It is working with the interrupt controller. So I guess, we'll just call out a pub function init 2 for now. Which, I should have seen this coming because the IO allocator is there. And what we'll do is we'll just do the part where we generate the interrupt vector table and stick it into the... and load it. So I think I can just do this. This is just generating my interrupt vector table and loading it, so hopefully this is good enough. Now, there's a lot of stuff that we're sidestepping here, but I think that's fine. Okay. So I'm seeing maybe the words no handler. So I think, okay, so I think what's happening is we're actually trying to log from 2 threads at once. I think one of these is panicking because there's no handler for an interrupt, and the other one is writing the word info in here. But I think if I look for no handler, that's because we're trying to like look up an interrupt handler for the interrupt that was generated. But what if we just don't do that? Okay. And in this case, we're just going to skip it instead of panicking. Now, do we see that halt wake up? So we wait 3 seconds. Let's go, baby! Okay, that's sick. That is sick. Ugh. So we've just figured out a mechanism that we can use to wake up a CPU from another CPU. Which means that we should actually be able to, if we actually look at the top output now, we should see that our 3 seconds that we're waiting for, we shouldn't see our QEMU maxed out on CPU usage. So let's go to like, let's just increase the time for that sleep. Right, we should see 10 seconds, and we'll up our number of cores to like 5 or something. And we should see that if initially our, yeah, QEMU is not using a ton of CPU here, not using a ton of CPU, not using a ton, then we should, after around 10 seconds, we see the sleep finished, hello me from CPU 1, and now we see that QEMU is now using 100% CPU, because that core is now back in the bad state. Okay. Okay, so that's looking pretty good. So we can say that we have like maybe experiment or enable interprocessor interrupts as a way to allow halt on second CPU. Okay. So now the next thing to do is try to do this like a little more formally. So properly enable ISRs on second CPU. And what else will we have to do? Once we have them like properly enabled, then we're gonna have to go through some form of process of like trigger IPI interprocessor interrupt when function sent to CPU. So I guess what that's gonna look like is we have this like CPU dispatcher. Here. And what he does is he just like pushes a thing onto a queue and the function onto the queue, and our application processor, he's just sitting here saying like wait for something to happen, right? And what he can just do here is he can just say halt here. And when he boots up, one of the first things that he has to do now is run this interrupt setup and then enable interrupts. So this will go in unsafe. It says create interrupts in it too. And this is core arch ASM store interrupt STI. STI standing for like store interrupt enable maybe? I don't know. I just know this lets them start happening. Now maybe we should be careful about which interrupts we have enabled, whatever, but that's fine. And then in our interrupts code, instead of just returning here, we'll just say info, maybe? Maybe we go back to panicking here, and we just enable, we register our special interrupt. So we'll say, what, main? We will go into our interrupt handler init, and here we'll just say, what, interrupt wake ups? No, where is this thing called? Interrupt handlers. Register an interrupt handler for IRQ ID internal. And we'll say we'll use interrupt 8090 for this one or something. 0x90. And he takes in a function. This is from interrupts. And expect failed to register empty interrupt handler. So the idea here is that we're trying to register an interrupt handler so that we can use this. We can like trigger interrupt 90. It'll run this function, which does nothing, but then we can use interrupt 90 as like our special magic flag here. So if I do interrupt 90 here, I think we shouldn't panic anymore. I think. Let's cargo run release and just see. Let's reduce that timeout from 10 seconds to like 3 or something. Give it a sec. Why is it just hung? I guess let's go back to doing this over here. We'll... Oh, yeah, obviously this is broken because this halt is here. Because we were in an intermediate state. So let's try this again. Hopefully I start seeing something interesting here. Okay, good. So we are not panicking. And if I punch in anything other than interrupt 90 here, we should start to see, we should see a panic again. 1, 2, 3, boom, crash, sick. Okay, so we have now flagged interrupt 90 as our like special interprocessor wake up thing. And so now what we should be able to do is in multiprocessing, we should be able to say, when we push something onto this queue, we then execute interrupt 90. So we'll just say send interrupt to the CPU ID that we tried to send to, the interrupt member, and we need the APEC pointer, I guess. So here we'll just store the APEC pointer. Which we can just store as a mwait now. And unsafe impulse sync for CPU function dispatcher. And unsafe impulse send for this guy. And then he'll take in the APEC pointer as a mwait. And when we construct him, we'll say CPU function dispatcher new. This takes in the APEC pointer. Okay. And he passes in the APEC, he like propagates this. And then when he sends the interrupt, he wakes him up. This should be a U8. Great. And so now in our boot processor, we can just halt every time we're done here. Core arch ASM halt. And he should actually unlock the queue at that point. And this is unsafe. Okay. So does that just work now? Let's go back to main now and change these guys to just say hello and exit. Oops. And then here, instead of doing the sleep stuff, we just, all of this stuff goes away. So the idea is now, since all of this is built, like all of the halt stuff is built into the CPU function queuing, what we should see is every CPU that's booted should print this info, and then just like sleep, take a nap. So let's try that. So each of these guys should do their info log, and they're not doing that. That's fucked up. So something's wrong here. What could be wrong? So we push the function back. Our application processor thing, he says halt time, and maybe we'll just say halting. And we'll also say wake up time. We did not enable the interrupt, so that would do it. Create interrupt init2, and then core arch ASM STI. We just forgot this part. Okay, now if I run this, I think we should see hello from here. We said halting, wake up time. That's good. And we don't actually see our thing run. I like the maze. Did you write it? Yeah, it was actually the first thing I did for the stream. I was like, the most important thing if I start streaming is that people don't get bored. And so we're going to write this. And there's like kind of like a series on it on my YouTube. if I go here, I do have like a playlist of me implementing this if you're curious. If you're curious. No pressure though. Yeah, it's like a Godot thing. We had some fun with like texturing and making it look like shit, right? Because like by default it wouldn't look nearly this shitty, but if I make it intentionally look shitty, then you kind of hide the fact that I'm shit at art. Yeah, all right. So back to this. So I'm trying to figure out why the fuck is this waking up not happening. So I do see that I am waking. I do see the info logs of wake up time. So that's good. But then why don't I see the info logs from within each thread? Let's maybe take put our CPU IDs in here to see if that gives me any extra information. So I do halt 1 and then immediately wake it up. But then why don't I see me running the functions? Like running functions for CPU ID. Like, what am I missing? So he says running functions, halting, wake up time, running functions, halting 1. Oh, okay, so he does halt 1 again, and then we just don't wake him up. Oh, it's because, like, we didn't enable the APIC. Where did that code go? Oh, fuck. Somewhere I had to execute that, like, right to the APIC pointer. So that's... Oh, I lost it. So that was... Here... I need to enable spurious interrupts on APIC. Now, the question becomes, how the absolute fuck do I get the APIC pointer here? And so maybe we have to find out, like, we need to do this reading on where the fuck does the APIC mapping come from? And so what they do is they intentionally, they like write this MSR, which I don't really understand. Okay, well for now, let's just get crazy. Let's get crazy and we'll just print line the APIC pointer ID and use it manually, and we'll clean it up later. Just to get like the bones in place. So we'll say let APIC print line APIC is the APIC pointer. Or to run. Okay, so here we get him, and we just say let APIC pointer is equal to this as mwait. We say the spurious interrupt vector is APIC pointer add f0 as mu32. We say let old val is, or we'll say let val is equal to the value that we read from this guy, ORed with 0x100, because that's what they said to do in the sample, and then we write that value back. And now, hopefully, we see that, like, we wake up. Yeah, here we go. Okay. 666. So let's just disable these info logs to reduce the amount of shit that we're seeing printed. But if I'm understand correctly, we do get our hello mic from CPU 1234, and now our QEMU is no longer just like spinning all of our extra cores. So that's pretty sick. Yeah, that's really sick. So what we've done is, without actually dispatching real interrupts to the secondary CPUs, we have enabled their local APICs to the point where they're receiving interrupts from interprocessor interrupts, and then all we do is we like send an interprocessor interrupt to that specific CPU. And so that like kicks it out of this halted state, which is pretty fucking sick. Because we've managed to dodge a lot of the complexity of the Apex setup, which is like dispatching of external interrupts to individual CPUs. But we've got enough where we have like our local interrupts are triggering. Yeah, I think I'm pretty stoked about that. Just to compare, before we were in this state where if we ran with 5 CPUs, we would be running at like 400% CPU all the time. And we didn't even, like, at the beginning of the stream, we couldn't even do that because our allocator was just like getting absolutely fucked by the lack of multi-core support. So I think we've actually made like a lot of good progress this stream. And I think we've kind of got the bones in place for, what's the word for this? Like a thread pool executor. So now that we have like a mechanism to sleep a CPU and a mechanism to wake it up, what we could do is we could kind of like in our executor for our futures, when we see more than one at a time, we can just pass them off to other CPUs and get them to run them as like a one-shot thing. So yeah, I'm pretty happy with that. I think I'm gonna call it here for today. I think we've got like we've done a pretty good amount of investigation, and I'll probably do some like cleanup. The thing that we're missing is the secondary CPUs are using like a cheat to get the Apex, as well as our like interrupt vector. We can probably share that a little better between CPUs. I don't think that's like particularly interesting, so I don't know. Maybe I'll cover that off stream. Maybe I'll get to tomorrow at 2 o'clock and be like, oh fuck, I haven't done anything since yesterday's stream, and I'll do it on stream tomorrow. But what I'm hoping to do tomorrow is start working on a thread pool executor so that our futures will be automatically dispatched to different threads. Thanks for watching. If you enjoyed what you saw, you can tune in most days at around 1 or 2 p.m. Pacific time, and I stream for like 1 or 2 hours. If you're watching on Twitch, you miss something, you can catch up on YouTube. There's a YouTube linked in my like Twitch bio, and if you're watching on YouTube and you want to come talk, chat about the OS, chat about whatever, say hi, ask questions, there's a Twitch link in the YouTube description. So yeah, thanks for watching, guys. I'll catch you on the next one. Bye.